segment, we're going to look at head-on collisions between two objects which do not stick together but bounce and move off afterwards. And the pretty neat thing about this is we're going to be able to handle objects no matter what their initial velocities are and no matter how elastic they are. So we'll use our usual convention that the velocities before are given by u, so ua and ub, and that's the before, and the after, their velocities are now called VA and VB, and they are unknown. So we can write down our conservation of momentum. And it's always a great idea to literally write down the law of conservation of momentum every time you use it. We have the masses times their initial velocities, and the masses times their final velocities. Now that's got two unknowns because we don't know the velocities either of them afterwards, so we can't solve, so we need a second law of physics, so the one we're going to use is Newton's experimental law. Which relates their relative velocities. So VB minus VA equals minus E UB minus UA. So we've got two unknowns, which are the V's, two equations, so this can be solved simultaneously. Now, before we look at all possible kinds of head-on collisions, we're just going to use our usual rule of taking a simple case. So the simple case we're going to take again is that one of the objects is moving and the other is not moving. We'll come back and do yet another derivation with them both moving a little later, and you'll see that we get pretty much the same answer. So here we are. So let's just draw this thing out again just to be sure. So there's UA, it's a number, and UB is equal to 0. Now let's apply the conservation of momentum and Newton's experimental law to this situation. So here we go. Equation 1 is going to be the conservation of momentum. So we have ma ua plus 0 equals ma ba plus mb bb. And equation 2 is going to be vb minus va, both of which are actual numbers, minus e, and then in this bracket just got 0 for one of them. The experimental law. And then we can rearrange the experimental law to give us a third equation for just one of those unknowns. So let's solve here for VB. So VB we can see is just going to be VA plus E UA. Now, we can take equation 1 and substitute it with equation 3 to get a solution. So let's see if we can do that. Substitute equation 3 into equation 1. So that gives us MAUA equals all right, that looks like it's right. Now let's multiply out this bracket, because what we're actually going to solve for, what's the unknown in this equation? The unknown we'd like to solve for is the velocity afterwards, VA. We see it appears twice. So if we can multiply out these terms and then collect all the VA terms on one side, we can solve for VA, and that will be our answer. So let's go ahead and do that. Okay, what can we do next with this thing? Now we can group the like terms. So let's move all the MA, all the VA terms together. So I've got a VA here, so let's leave it where it is. MAVA. And I can move this other term over here, move it down here. So it becomes minus right, and then we'll move the UA term over here, so the UA terms are all together. MAUA minus MBEUA Now I can isolate my common factors on each side, which in this case are UA. So I've got MA minus MB times E, and over here I've got VA as a common factor, MA plus MB. And then one stage left to do, and we've got our solution. Sorry. That thing is all times UA. So that's kind of our solution. We can solve this for VA, and then once we've got the answer for any actual problem, we can go back to equation 3 and solve for the other velocity, and we'll be all done. So that's the solution. Now, let's just look at 3 possible cases. Imagine that E is equal to 1 for a perfectly elastic. Now look, what have we got? So now VA, I'm just going to take this whole equation and put E equals 1 and just see what we end up with. MA minus MB over MA plus MB all times UA. So that's our relative velocities and our final velocities in the case of perfectly elastic collision. Now let's look at an inelastic collision. Inelastic means that E equals 0. So now we have VA, E is 0, so what do we end up on the top? End up with just MA, because 0 times MB is 0. MA plus MB times UA. And then we can look at the general case, which that is the answer for the general case, where E can be anything, somewhere in the range 0 to 1. Then we can look at another set of cases. Let's consider, what if the masses of the two were equal? So let's look at equal masses in each of these 3 groups of solutions: the perfect case, the perfectly inelastic case, and then the general case. So let's take our equation here. What happens if MA equals MB? Well, now MA plus MB is just an MB. They're both 1. And then on the bottom we have 1 plus 1. And this is all times UA, which means that our final answer then is 0. Which is kind of interesting, isn't it? This says that if 2 objects of equal mass, one is stationary, one runs into the other one, that the first one that was moving will come to a complete rest and give all of its momentum to the other object, which means we can then trivially solve for the speed of the other object. So that's pretty cool. So that one's done. Now let's look at the completely inelastic case, where E is equal to 0. And both masses are equal. Let's draw a line across here to separate these. So here we go. Let's take this equation here, make E equal to 0, and what do we now have? Well, we have 1 over 2, because 1 plus 1 is 2, and that one there is 0, so we've got a half UA. So this suggests that if 2 equal masses run into each other, stick together and keep on moving, that the combined mass will move off with a speed equal to half the original speed, which is interesting because it's exactly the same result we got in the very, very, very first case that we looked at with conservation of momentum. And now we'll look at the general case. E is equal to any value, but the masses are equal. So this is the last one we're going to do in this lecture. So now VA equals, so let's see, MA is 1 because the masses are equal. E is equal to anything, so it's still E. So that's 1E, so I have 1 minus E. On the bottom, I have 1 plus 1, and this is all times UA. So finally, I have 1 minus E over 2 UA. So that's the general solution for 2 objects. One is stationary, one runs into the other one, and then they collide, bounce off, and do whatever happens. And this solution will be the case for all of them. So we are done.